You will not
The bottom line while we're waiting for my presentation to come up. There have been some fairly incontinent attacks on Lovelace's reputation. And my bottom line is much the same as Doran's. I want to present some hard evidence that these incontinent attacks, universal, or on a kind of universal plane, I want to present you some concrete, hard evidence that these attacks are not warranted. There are people who I read when I first started getting into this, who I read when I first started getting into this, and I really have no right to be here. I think I was asked I can't remember when Ursula asked me, and I think it was only because I was boasting that it was the 50th anniversary of me writing my first computer program. And Ursula, in the way that those of you who've worked with her will know, bounced up and down and said, "Oh, you're just the person to convey Ada's excitement in presenting the details of the analytical engine." So maybe I was just the person, or maybe I wasn't just the person. But I went on what you might call a, where's the, here. Have you got a, thank you. Does that change it?
Yes, it's working.
Which is the button?
This is the microphone.
Oh, this is microphone. Okay. Thank you. Please. 50 years of program and I still can't press buttons. Thank you. Okay. So I went on what you might call a programmer's journey of discovery. So how many people are programmers sitting here? Oh, damn, there's enough of you, right? Okay, so you're going to understand, you may understand more of what I have to say than I might have been expecting you to, in which case I apologize for any of the technical mistakes. Here, incidentally, is a piece of paper that I wanted to hand out to you. And what you would see on the piece of paper, which is actually reproduced as a fold-out in the inside of the stuff that you got in your goodie bag, and at some point I'm going to be referring to it. This, in the end, is going to be the object of the study. This is the table for the computation of the Bernoulli numbers. So we're going to see if we can take the programmer's journey through Ada's paper, learning, as I did, a huge amount about the analytical engine. I only knew Ada's reputation. I only knew what Ada had done in the same way that probably 90% of you sitting here knew it. She wrote the first programs. The DoD named a programming language after her. She was the first computer programmer. Those of you who are more inclined to be sympathetic to general notions of heroics and visionaries will also have digested what I didn't know until I started reading the general literature on her, which is that her reputation as a visionary, a pioneer, the person who essentially did it on her own. And as I think Doran's pointed out extremely well, she didn't exactly do it on her own. But here's some of the stuff that she did that impressed me as a geek, an aged geek, long-term programmer, reading through essentially the documentation. And I urge every single one of you, I urge you all, the logicians in the audience will understand the difference between those two statements. I urge you all to go read the paper. There's a huge amount in it. There is, whoever you are, there is a thread in this material that you will want to pick up on. If you are historically minded, part of one of the threads for the historically minded is the way that you'll find yourself as a historically minded geek getting incredibly impatient with well, you're all programmers. I don't know whether the people who subscribe to the heroic school are going to take this lying down or not. There's an overwrought to some of the language in the paper. One of the things that I found difficult as a geek in getting to grips with what I had to get to grips with was there's a procession of facts, and then there's a long philosophical disquisition. Eventually, you get back to the facts. In other words, Ada writes more or less how I lecture. So I'm going to... Okay. So here's the warning up front, which I've not completed. I'll complete it at the end. Roughly speaking, what she says is you get very excited at the beginning when you're considering a new subject. You overrate it like mad, and then by a natural reaction, you undervalue the true state of the case when we discover that our tenable. Some of the incontinent attacks, I think, count as underrating, and some of the stuff that I'm going to say today, I hope, will be a sort of partial defense, anyway, of Lovelace. Another part of the bottom line, in case I rabbit on for far too long, is that Ada was a programmer, that this, despite the fact, and of course you can't see the little red marks, despite the fact that there are errors in the table, works. It is not a program for producing the Bernoulli numbers. It is a scheme for a sequence of programs, each of which will produce the next Bernoulli number. Okay. The reason that it could not be a program is that the machine, which never existed anyway, it's abstract in more senses than one, never had a facility for calculating places in the store. Maurice Wilkes put it best. Many of you will know who he is, and those of you who don't, it doesn't matter. Maurice Wilkes put it best. He said, the numbers of the columns, the V0, V1, V2, V3, those numbers were just names, right? 0, 1, 2, etc., were not addresses that could be calculated. And this is the fundamental limitation of the machine, and it's the fundamental limitation of the program. We'll get to that in a second. So, what are you going to get if you're a programmer, which I was, reading the paper over the last few months? A kind of blurred snapshot of Babbage's developing idea of the analytical engine. You can tell when you're reading Ada's notes that she's not writing about quite the same machine that Manabria's paper describes. And there's some tension there. You know, we expect to read things that are in some sense coherent and consistent. And, you know, 180 years after the fact, I can't do the arithmetic, somebody do the arithmetic. You know, 180 years after the fact, nearly 200 years after the fact, that's good enough, isn't it? We're now used to seeing things very focused. And when someone writes a paper or presents a paper, you're expecting to see consistency between the beginning of the paper and the end. And you're very uncomfortable, especially as a programmer geek like me, when you see something at the beginning that's not quite the same as something at the end. And you have to learn to live with this. And I haven't quite, which is one of the reasons for my overexcitement at the moment. You'll see several related notations for programming calculations in the engine, calculations for the engine. And if you'll forgive me, I'm going to continue to call them calculations, because until we get to the punchline, you'll see that that's what they actually are. I mean straight line calculations rather than algorithms. There are suggestions of algorithms, but what's in the tables are straight line calculations, something you could do on a programmable Hewlett-Packard calculator which didn't have loops or branching. Okay. So, and you're going to see, as I say, you read, as you'll see if you read it, the derivation of an algorithm and its near implementation as a program for the engine. Okay, so here's the context. I think it's important to understand context, particularly when you do this kind of time travel. Okay. If you talk to people who don't know algorithms and who don't know algorithmics, they'll tell you, oh, Ada wrote the first algorithms. Okay, you know that she didn't. the first algorithms were probably written by the Greeks or the Babylonians, expressed by the Greeks or the Babylonians. Okay? There were certainly some non-trivial algorithms, and they'd been studied for a long time by the time of the Greeks. But between the time of the Greeks and Ada's time, mathematicians really never developed a proper notation for describing dynamic processes. Roughly the best you could get was sort of recurrence relations. And that was fine. But control was always expressed in a very informal way when you were describing algorithms. Here's another part of the context. This is a context which I hit first when I came to study the paper, or to read the paper anyway. So Alan Bromley was a very distinguished engineer who studied Babbage's drawings extensively. Maurice Wilks arguably designed the first computer that ever produced that ever delivered a proper computing service to non-computer experts. I mean, he called it a computer service. His reputation rests on that. There are other aspects to his reputation that we can talk about privately, but his scientific reputation rests on him having developed EDSAC and so on. Anyway, so this is Alan Bromley writing to Maurice Wilks when Alan Bromley was already kind of sick, although he'd done extensive work on Babbage's drawings. He says, "I've just worked again through Babbage's notebooks concerning his work on the engine. I've been greatly disappointed by what I've found. Through most of the period, the operation cards provided for only 4 operations: addition, subtraction, multiplication, and division." Well, we know that's enough to do the kind of calculations that we want to do. What is the only there refers to the fact that there are no realized mechanisms in the machine for allowing a user-level programmer to write conditionals or loops. That's where his disappointment rested. And it's a curious disappointment. And it's a curious fact that Babbage, although he could perfectly well write what we would now call microcode, which had loops and so on. Indeed, you saw the loops, the barrels going round and round. That was not offered, I think this is fair, isn't it? It was not offered, that is to say, Babbage never developed the machinery to enable this to be offered at the programmer's level. This is Bromley's disappointment, okay? There's another physical fact about the machinery that needn't detain us now because it's going to detain us a little later. Okay. So Menabrea says very early on in the translation that the machine's not a thinking being, it's simply an automaton. Babbage had to work really hard on devising machinery to do things like division. Okay? What Menabrea is saying is, but you don't have to know how he did it. If you read a little lower in here, it says, "Under the impossibility of my here explaining the process through which this end is attained," that is to say, the full arithmetic, done by now what we would now call microcode, "we must limit ourselves to admitting that the first 4 operations of arithmetic, can be performed in a direct manner through the intervention of the machine." That's it. Here we have the detachment in Menabrea's paper, translated appropriately by Lovelace, from the machinery. This is what makes our discussion a discussion now of an abstract machine. Lovelace says something similar. Indeed, she's contrasting Menabrea's presentation of the abstractions of the machine to an exposition given by Dionysius Lardner, another scientific writer, who had written essentially an anatomy of the machine. Okay? He described the machine at the physical level much in much the same way that Doran described Babbage's presentation of the machine, essentially discussing the clinking and clanking of the machinery. What Lovelace says is, you don't need to hear the clink and clank of the machinery to understand the machine, to understand what it does, to understand its function. Okay? Monsieur Menabrea on the contrary, exclusively develops her spelling, not mine, the analytical view, taking it for granted that the mechanism is able to perform certain processes, but without attempting to explain how. Every computer scientist teaching your first programming class, that's the kind of thing you want to say to the students, isn't it? You don't have to understand, how the bits and bytes are arranged, or, what the bus does. You just have to take for granted that this is what it does, and we operate at the level of the abstract machine. We might sometimes say the virtual machine. Lovelace clearly understood, and something that Doran said in his presentation made me think that she may have been thinking of herself and of Babbage when she wrote this. It is obvious that in the invention of a calculating engine, these two branches of the subject, mechanism and function, what it is versus what it achieves in the abstract domain, mechanism and function are equally essential fields of investigation, and that on their mutual adjustment one to the other must depend all success. They are indissolubly connected, though so different in their intrinsic nature that perhaps the same mind might not be likely to prove equally profound or successful in both. Now, if you want to have a little metaphysical fantasy here, you can think, she's thinking of Lovelace and her. She does function, he does structure and clinking and clanking. Okay. So he's getting on to the business now. This is Menabrea. And what he's describing here is, and the interesting thing here is, if you only read the paper, as I had, I'd never seen any drawings of the analytical engine or anything. In fact, the first time I saw the connection between the machinery that was going to clink and clank and these columns called V1, V2, V3, etc., was when Doran sent me his slides on Saturday afternoon. I thought, of course. But that's what you think, isn't it? Okay, in general, we have a series of columns consisting of disks, which columns we will designate as da-da-da. We may require, for instance, to divide the number written on the column V1 by that on the column V4 and to obtain the result in column V7. Well, now, everybody else who's ever read this paper or read anything by anybody who's read the paper, or anything by anybody who's read anything by anybody who's read the paper. This is the way that knowledge about the paper is transmitted, incidentally. Few people appear to go back to the paper. I went back to the paper, so you don't have to, but actually I recommend that you do. You find out, this is interesting. We're dividing the number written on the column V1 by that on the column V4 and obtain the result in column V7. It's a three-address machine. Well, sort of. Okay? To effect this operation, we must impart to the machine two distinct arrangements. Through the first, it's prepared for executing a division, and through the second of the columns, it is to and through the second, the columns it is to operate on are indicated to it, and also the column on which the result is to be represented. That's true too. Three-address machine. Knuth even describes it as a three-address machine somewhere or other in his description of early algorithmic notations. One specifies the operation, the other specifies the operand and result columns. We need not detain us here in understanding how it is, I think, and you can tell me whether I'm right or wrong, how it is the arrival of the result comma address that triggers the mill to do its business. But maybe that's wrong. Tim?
Yeah.
Is it right?
Depends on which version you look at.
Okay. Yeah, we should have acknowledged Microsoft earlier on. They would have said the same thing about his PowerPoint, right? Okay. The two mechanisms must be distinct. So here, as someone who's really into the abstract machine, you're being presented with a concrete detail of the machine, which is a bit disturbing. What does he mean, the two mechanisms must be distinct? Meaning the mechanism for imparting the operations, setting up the mill, the mechanism for sending the operand addresses that we would call them, or actually the operand names as Wilkes would call them, and the result. If this division is to be followed, for example, by the addition of two numbers taken on other columns, the two original arrangements of the machine must be simultaneously altered, that is to say, the opcode and the operands. If, on the contrary, a series of operations of the same nature is to be gone through, then the first of the original arrangements will remain, and the second alone must be altered. Okay. So you've got a series of multiplications. You set up a multiplication, and then you start streaming the operands and the results to it. Or maybe even you only stream the results. If the operands are the same and you sending the result to the same place, to different places, maybe that works too. You don't, as a programmer, you don't want to know this detail. You really don't. And actually, the great achievement of Lovelace, if you follow through the paper, or maybe it was Menabrea, but anyway, between them, they managed to convince you that it doesn't matter. Okay? So here we go from, in Menabrea's paper, a very concrete detail of the clinking and clanking, as we'll see. We've got 10 minutes, right? Okay. And I'm nowhere near the algorithm, I say, right? Oh, well. Okay, so. Okay, let's just look here. The details almost don't matter. Doran showed you some of this anyway. You see there, he's calculating, Menabrea's table is calculating, in this case, it's just part of the, he's calculating the x as part of the xy solutions of these two linear equations, okay? What you need to look at here, I'll point you at it, is, you see there's four multiplications. Different operands, different result locations, then two subtractions, and then a division. Okay? Now look. This takes 3 operation cards if so desired. So here in Menabrea's paper is something that turns out to be distracting and a bit of a red herring through some of the rest of the presentation. I don't want you to be distracted by that when you eventually get to read the paper, as you all will. Okay. Lovelace, in giving her account of the general purpose nature of the engine, I at first thought, because I have to say I'd paid more attention to the incontinent attacks than I had to the paper for a while, and I abase myself in front of the fandom for having done that, but I hope I'm going to redeem myself. Lovelace, I thought, found it a major distraction. Anyway, here she's doing something very positive, explaining the general purpose nature of the machine. Here's what happens if you have written in the at the bottom of the column. At first she thought, that if you wrote A at the bottom of the column, then A would be on the bottom of the column. That's a memorandum. That's what a computer scientist would call, that's the abstraction relation being written there. So she writes A, N, and X. So the variables on those columns are A, N, and X. She's beginning to describe the programming notation that she's going to use a bit later. Okay. Whatever the variables are, you can compute a variety of different functions of A, N, and X. And she gives us several, but here are two that I took. To calculate AX to the N with these variables on its columns, it requires 6 multiplications to get X to the N, and one multiplication to get A times X to the N. And now there's a curious use of notation here. And at first I thought, what is, you struggle with this. You say, what is she doing? And you see there that, yeah, there are 6 multiplications, okay. But they're not 6 multiplications that arise necessarily from the structure of what's been written. So writing it down as 7 times is a bit strange, okay. And you see this from time to time where there is a counting of operations, and because you don't know what the variables are going to be, you don't know really what the program is, okay. This may be where the slogan science of operations started to emerge. Fortunately, it goes away again. As you read further, you see that this distraction doesn't matter. For X times A to the N, the operations will be, well, there will be 34 multiplications there. Okay, but she's saying it's it's hard to detach yourself from the idea that really what she's saying is 34 times is what you need to do, not 34 multiplications is what happens. Eventually, you get away from it. There's Menabria's complete table. Here's a simplification of it, where I have brought out something that sits there in the notation, but it sits there very quietly in the notation, which is that when a variable appears as an operand, there's two ways of referring to it. In one way, it just means the variable and the variable column with the variable column stays the same once it's been sent to the mill. And there's another form, which I've underlined in blue in this calculation. The precise role doesn't matter there, where those blue mentions denote a reading and then zeroing of the column. This is going to prove decisive in one of the mistakes in the table. Okay, Rainer, I've corresponded with you, but I don't know where you are. Can you put up your hand so I can see? Rainer?
What, please?
Ah, you're Rainer.
Yeah.
Hello, I'm Bernard. All right. Right. So I'm about to describe some work that Rainer and I essentially did along parallel tracks, and then Doran introduced us, and we discovered we'd been coming to the same conclusions, namely that there were mistakes in the... I'm going backwards. I should be going forwards. Right. Okay. So by the end of the first phase, before you hit note G, you've begun to get the flavor of the way in which she is describing as a table the machine codes of the program, the instructions of the program. I've essentialized this. I've discarded quite a lot of... There's the same height above that of stuff showing columns with zeros on them and so on and so forth. It's another kind of distraction. You wonder which. Anyway, so just let's try and understand the Bernoulli number table in the... How long I've got left? 5. Ha! Right, Richard Bornat was right. Too much material. Okay. However, I listened to him and I put the conclusion first. Okay. So what the table actually demonstrates is the computation of B7, given that B1, B3, and B5 had already been computed. Okay? So actually, I sort of disagree with Doran, because as you read down the side of these tables, there is an implicit sequencing there, okay? And all of the straight line calculations we've seen so far, everything that didn't have a loop in, that implicit sequencing is enough, and if you'd put each of those things on cards, that would have been enough too. Right, but here's where she begins to show that she differs from Babbage in her view of what the machine can do, okay? I mean, can do mathematically even, right? Independent of what interpretations you give to them. Okay. So why would you do that? Why would you not try and describe a general program, right? You know, why don't you write the precondition, the loop invariant, Okay. This style of explanation goes right back to Babylonian times. If you look at how Babylonians explained algorithms, they give you very concrete description of a particular calculation, and then by the side, you'll see the generalized explanation of what is going on. This is mixed in the object of our study. As you'll see, open the inside of your goodie, and you'll see there is both a concrete description of what the particular calculation she's talking about. And there's something disconcerting here. It says, it looks like this touch panel has lost connection. Right. Okay. But what her intention is and her explanation is, her discourse about the table, it's okay. It's okay. It was just, I was telling the truth, but it was sort of a pleasantry. Right. So Lovelace's intention is to show that the table can be interpreted more generally. And certainly Rainer and I independently and then together, despite noticing bugs in the table, we've shown to our own satisfaction, and I think it would be to your satisfaction if we had the time to explain it, that this is the case. Certainly, I now believe that if the engine had existed, Lovelace would have noticed the bugs very quickly. So you're nearly all programmers. Hands up those of you whose first program, you know the end of this sentence. Okay? I do remember my first program, actually. I'll tell you about it. There are endless stories I can tell. I'm just, you know. Anecdotage is a word that could have been coined for me. Okay. Had the engine existed, Lovelace would have noticed the bugs very quickly. The really curious thing here, and the thing that is irritating, I think, to Doran, to me, to Rainer certainly, is that since this hair was started in this book, Hartree's book, that this table denoted a program and that the program computed the Bernoulli numbers, nobody's gone back to the table and tried to verify, or at least examine, whether it computed anything remotely like the Bernoulli numbers. They've taken, right? I mean, here Hartree, professor of, you know, what these days might be called computation at Cambridge, says, the evaluation of the Bernoulli numbers from this recurrence relation is programmed for the analytical engine. This is the end of his stuff on Babbage's analytical engine, right? So he credits Ada with producing this, producing the table, just says, bang, it does it. Everybody else who's written about this, including the editor of the important volume Faster Than Thought, that's Bowden, E.V. Bowden, isn't it? Seems to have gone back to that and simply taken at face value that claim. Now, it's true and it's not true in the way that your program works and it doesn't work, right? What I mean is, I'm not talking about Schrodinger's program here. We do give an explanation. I'm not going to trouble you by taking you to the end. We simply believe that she would have noticed the bugs very quickly, but we are mystified at the fact that there has been no acknowledgement of the bugs, which are significant. I even looked into the literature. I read a lot in the literature. I read a Russian paper. Sorry, I read a translation of a Russian paper. You know, I can't lie in front of my co-authors, right? I read a translation of a Russian paper which claims, you know, we translated this program and it runs. Okay, but that's not what they did. That's not what they did. Okay? If they had translated the table back literally as a simulation, which is what I did at first, it's where I began to have my doubts. You know, I'm trying desperately to understand what is going on here. I wrote a desperate letter to Doran saying, hey, Doran, has anybody actually run this? Right? I sent a courtesy copy to our organizer who said, haven't you guys got something better to do than to find errors? Right. Bless her. There is something better to do, which is to say, if the spirit of the programmer had been followed here, and if she had been allowed to find the mistakes, would the program have run? And the answer there is unquestionably, in my mind, yes. And actually, I'll go further than that. She struggles. She argues at the end that although she's given you a very specific description of the state of the machine having computed V5 and about to compute V7, and really, the part of the table... Oh, there's some Bernoulli numbers, by the way. Right. The reason I show you these is that some of them are slightly under 50 digits long, right? And some of them are unquestionably not. So there's a whole other thread here for the numerical analysts in the audience. Hands up. Which is actually just how far could the computation have gotten in calculating accurately these values. I've shown them as rational representations. I thought that was the safest way to do it. What she says is, by using this recurrence relation, we do a first series of computations that essentially computes B1, second series of computation that computes B3, a third series of computation that computes B5, and then that third series of computations, which is what I describe as the body of the loop, will compute any Bernoulli number from all of its predecessors. She argues very strongly that that is the case, and she makes her case. When you read the paper, or at least when you read my paper or Reiner's paper, you will see that that is the case. And I think we should applaud her for that, and also her observation at the very, very end of all of this, which is, you see, God, you were right, Richard, right? Here's what she says. It's interesting to observe that so complicated a case as this calculation of the Bernoullian numbers nevertheless presents a remarkable simplicity in one respect, viz. That during the processes for the computation of millions of these numbers, no other arbitrary modification would be requisite in the arrangements, excepting the above simple and uniform provision. She's inventing loop body abstraction. Uniform provision for causing one of the data periodically to receive the finite increment unity. Very last word. I programmed a simulator which equipped the machine with this ability to sequence through tables, in other words, turning numbers of columns into addresses of columns. I literally took her literal but slightly corrected program. I mean, there's a couple of places where it's wrong, but not drastically wrong. Ran it, and, well, okay, so we actually went up, I showed you some Bernoullian numbers. We went up to about B991, okay? And then my patience was exhausted, and yours is now. And thank you for listening.